Unit 6 is a long unit. I was going through the packet to write down notes, and it was like 70 pages. It's a lot of content. And like some schools, they do it all as one unit. They do Unit 6 and Unit 7 as just the rotation unit. So it's a lot, right? And it's hard. It's hard stuff. So I'll start off by saying this: if you want to like master this unit, like watching these videos are definitely gonna be helpful for like a conceptual understanding, but you gotta practice. There's just so much things that I can't cover because this video would be 2 hours long. You gotta practice and just kind of face all sorts of different types of problems. Rotation, like these problems are really complicated. There's a lot of different types of problems. I'll go over a lot of the main stuff though. And just to start with like that conceptual background, like what even is torque? It's kind of hard to explain. I've never really found a good verbal definition. And really, just to think about torque, we gotta go back to our first day of the unit. We had the watch glass, and we had the meter stick, and we had to like figure out what are some ways we can place masses, right, so that everything balances. And we can get all sorts of combinations. You could have a bunch of masses here, and then you just have your axis, or not, sorry, your watch glass like right here, and then everything balances, right? You can have a bunch of heavy stuff would have to be closer, lighter stuff would have to be farther, and we're just figuring out all sorts of ways to balance this meter stick. And I'm gonna use a green marker. This one is kind of dead. What we realized is that, well, in order to balance this thing, we don't necessarily need equal forces. Like right here, you can see there's a whole lot of all the weights are pushing down this end. There's no weight pushing down here. Like there's no weights that are pushing down on the ruler. So the forces don't have to be equal in order to balance. If you have forces on both sides, the distances don't have to be equal, right? This distance is obviously be greater. So then what makes this balance? Like there has to be some sort of equal quantity, just like if we think about it, right? Equal forces cancel each other out. So what's the equal thing? What's that quantity that causes everything to be balanced? And that's where we learned torque. So that is what torque was. So, that's not what torque is. That's a terrible definition. Torque is really the rotational version of a force. I don't know if I love that definition. It's the ability to make things angularly accelerate. So if we had a mass, right, that was moving at this speed, what do you need to apply in order to keep it moving? You don't need to apply anything. You don't need to apply a force, right? It has inertia. It'll keep following that velocity, and a force is gonna accelerate it. So it's gonna speed it up, slow it down, or whatever. Torque is going to rotationally accelerate something. So if this is at rest, as long as there's no net torque, then it's not going to accelerate, it's not going to angularly accelerate, it's not going to start rotating, it's going to be balanced. It's like that rotational version of a force. It's not a force though. Torque is not a force. It's like a force in the sense that it causes angular acceleration. So, one lab we did, just to kind of keep refreshing your memory on this stuff, to get that conceptual background. One lab we did is we had, I don't know what you call it, there was like that clothing hanger thing with all the hooks and stuff. And then we had a mass here, and it was just like a set, maybe like, 20 centimeters or something. And what we did is we took a spring scale, or like a force sensor, and we kept putting the force sensor in all sorts of spots, and from varying distances. So if we were to, our independent variable was the distance, we kept changing the distance, and we saw what was the force required to keep it balanced, okay? So here, in order to keep everything balanced, I need to apply a certain force, and then here, in order to keep this whole thing balanced, I need to apply a certain force. What we found was that it would make an inverse sort of shape. So what is it saying? It's saying that from the middle, right, if we went farther and farther out, the force required would be less. We would need less force for a greater distance. And as we got closer and closer and closer to the center there, we needed a greater force to keep everything balanced. And if we linearize this this graph. So we had force, and then 1 over distance. There was a slope. All right. Now this slope had a unit of Newton meters. Did it? Didn't have a unit? Did it have a unit of Newton meters? Yeah, it had a unit of Newton meters. I'm just trying to make sure with the force. So newtons divided by 1 over meters. That would be Newton meters. And the value, every group did this, the value they figured out was the mass times, times gravity. So the weight of the mass times the distance from its own center of mass. So this mgd is like the mass of this thing, which is constant, times g times the distance, which is also constant. So this was a force times distance. We figured out that the slope was actually the torque by this weight. So in reality, what we figured out is that if we want the torque on this side to be balanced, we need the torque on this side to be balanced, which is going to be whatever force we apply times distance. So as a distance, because this is constant, this torque is constant, it's a constant force, constant distance, a higher distance allowed us to get a lower force. We didn't have to apply as much force for a greater distance. That was really how we kind of figured out that torque is equal to force times distance. So that general equation is that the torque by a force is the same as the force itself times the distance. And we call this distance, people call it all sorts of things. I call it the lever arm. I just like calling it the lever arm. It's the, I don't know why I like calling it, it just has a nice ring to it. It could be distance, it could be, it's not radius, right? It doesn't always have to be radius because, you know, that doesn't make sense. Like, how is the radius of anything? It's just the distance from the axis of rotation, and that's a whole other thing we got to talk about. But that is kind of torque, that's kind of the basics of torque when we first learned how to keep everything in equilibrium. So, let's talk about, actually, yeah, I'll just quickly define. Axis of rotation is the axis at which something rotates. So, right here, from this side view, it looks like a point. Like, right here's the axis of rotation, right? Because that's when it starts swinging. But it's not really a point. If you think about, like, a merry-go-round, although aren't those fun? If we have a merry-go-round and it's rotating this way, the axis of rotation, it goes through the middle, but it's like a whole axis. Like, it's like spinning, like, about an imaginary line. So in this case, that line is like, it's like shooting out of the board, basically, right? It's like, if it's swinging like this, the axis of rotation is this way. It's like rotating about that axis. So it's an axis, it's not a point. And that'll be important for later on. This right here really set us up for equilibrium problems. In my opinion, these are the hardest problems in torque things. In all multiple choice, in all all FRQs I do, and all multiple choice I do, I usually get an equilibrium problem wrong. They're hard because there's just so many things. So let's take a look at some of them. So let me just take a look at the time. I just want to pace myself. Okay. So for an equilibrium problem, you can have all sorts of things. The whole idea is that nothing is rotating and that nothing is accelerating, and it's at rest. So if you have like a beam or a seesaw, let's just have a seesaw. You can figure out, like, if everything's at balance and you have one kid here at a distance of 4 meters and one kid here at a distance of 2 meters, you can figure out the mass of the kids just if you are given one of them. The reason for that is because everything's at equilibrium. So we know if this is our axis of rotation, right? Whatever torque is here, right? There's going to be the torque by this kid. So force kid. Not Fg by kid, right? Because Fg, that's between the earth and the kid. We're worried about the force on the board. So there's going to be like a push force, like a normal force by the kid on the board. There's also going to be a force here. There's going to be the force of gravity by the earth. There's also going to be that normal force. There has to be a normal force. I forgot that there was a normal force when we first learned this. Like, yeah, there has to be a normal force by the fulcrum that has to equal all of these forces combined so that nothing is accelerating down. There has to be that upward force to keep everything stable. Okay, so let's say this kid is 10 kilograms. Okay, we gotta figure out what's the mass of this kid. So we have four forces. We have force normal, force gravity, force kid 1, and then force kid 2. So I'll just write those down. Force gravity, force kid 1, force kid 2. Some of these are going to cause a torque, and then some of them are not. Force normal and force gravity don't cause any torque. So I'll say like T net, or not T net, T torque, tau actually, tau Fn, and then torque Fg. Those are 0. The reason they're 0 is, remember, torque is equal to force times the lever arm. There's no distance, there's no lever arm from the axis of rotation. It's right at the axis of rotation. So this is 0, which means this is 0. So no torque. There's going to be the torque by F kid 1. That force, force F kid 1. F kid 1. And then there's going to be a torque by F kid 2. So force F kid 2, and then times their respective distance. I'll say lever arm 1 and then lever arm 2. So yeah, there's going to be those two torques. Now they have to be balanced. So this, let's think about it. This force is going to cause a torque counterclockwise. I'm doing this by literally just curling my fingers about the axis of rotation and then seeing, oh, it's rotating this way. You can also have, if this was your seesaw, the kid here would cause counterclockwise rotation, and then this kid would cause clockwise rotation. So the counterclockwise torque and the clockwise torque have to be balanced in order for anything to be in equilibrium. So I know the torque by kid 1, or F kid 1, is going to equal the torque by F kid 2. So then what I can do is I can just plot in, okay, F kid 1 times lever arm 1 is going to equal force kid 2 times lever arm 2. And then the thing here is that this F kid 1 force, it's just equal to Fg of the kid. The reason for that is because this force is going to be exerted equally on the kid, right? Because the kid is going to have that equal and opposite force on him. So there's going to be that F kid 1 upwards. So the Fg is going to be equal, so that the kid is not accelerating. So boom, bada bing. And then once you know the mass, you can actually just figure out, yeah, what's Fg kid? I know the distance, and I can figure out the other distance. This is 4 times more away. You can mathematically figure this out, but I'm just going to tell you it's 2 times farther away because it's 4 meters, 2 meters. So this has to have 2 times the mass, 20 kilograms. I just did that in my head, that's what you can just figure out mathematically, just plugging everything in. So yeah, that's that's one equilibrium problem. I might have to make this 2 parts because this video might get long. Yeah, that's equilibrium. That's the SCP-5 of equilibrium problems. You can figure out some stuff. Let's get into SCP-6 real quick, or SCP-4 and 6, because equilibrium problems do come into play there. So if you had a question like this. Alright, we have to draw an FBD for these boards. There's this diving board, and then there's this diver, and then there's the FG of the board. And I'm just drawing that in, because I know there has to be an FG on the board, unless it says it's massless. That's the first force you can draw with 100% confidence, because you know FG is always pointing down, and it's going to be on the board, so it acts at the middle, the center of mass. And that's another thing. Center of mass from Unit 5 we talked about. It's just the distribution where the mass is sort of, it's, what's the word? I guess the average location of all the mass. It's where you can, FG always acts at the center of mass, because FG really acts at every part, and then it kind of all equals the center of mass. I don't really know how to explain it, because I don't understand it too well, but it always acts at the center of mass. Fg. So how do we figure out? Well, the torque has to be equal. One common thing that first off the bat we might think is that okay, these have to cause normal forces this way, and then obviously the F kid has to push down. So obviously the F kid does have to push down. Okay, so the F kid does have to push down, because obviously it's impossible for it to push up. Now, first of all, let's think about this. If our axis of rotation, and this is where things get complicated for me, if this is our axis of rotation, then Fg produces no torque. F kid is going to produce a clockwise torque, and then our these two Fn's will also produce a clockwise torque. Just because these balance, like just because there's two forces up and two forces down, doesn't mean the torque's equal. Because these cause clockwise torques. So, you got to keep that in mind. Obviously, you can't have there's no way the net torque is going to be equal if you have two clockwise torques. There has to be some sort of counterclockwise torque. Well, how could that be possible, right? What could cause that counterclockwise torque? Well, the board is going to be bolted. So in this case, like there's going to be these bolts that are actually that can cause a downwards force. So now with that in mind, how can we make this no net torque? Let's start with one possibility. Okay, we don't know the values of the forces, so we could say, oh, well, maybe this force is upward and this force is downward. Let's start with there, right? And this is where guess and check kind of comes in, because what you can do is you can say, okay, this is our axis of rotation, the middle. Therefore, this is going to cause a clockwise torque. This is still going to cause that same clockwise torque, right? It's going to push it up, but this force is going to cause a counterclockwise torque. So this force can balance out these other two, or this torque can balance out the other two torques. That's not unreasonable, right? That makes sense. But when this is our axis of rotation, there's gonna be clockwise torque, because Fg, right, is now not this is not the axis of rotation, so Fg will cause a torque, F kid will cause a torque, all in the same direction. Things are gonna rotate this way because this force no longer produces any torque. So now you got to check a whole bunch of axes of rotation, right? Maybe then this force would have to point up, right? So then, therefore, the only other option for now, if this was back, our axis of rotation, if we put that back, now this force would have to point down, right? And then now we can check all axes of rotation. This is our axis of rotation. Okay, two counterclockwise, one clockwise, everything balanced. This is our axis of rotation, one counterclockwise, two clockwise, things are balanced. And if this is our axis of rotation, one counterclockwise, two clockwise, and it's really just like checking every axis of rotation. And then you can do the math, right? Let's say you don't know this force, and you want to figure out this force. Okay, you don't know this force. You want to figure out this force, and then you want, like this mass is maybe 10 or something, and then this kid's mass is like 20, whatever, and then maybe you know the distances and stuff. How do you figure out one of the forces if you don't know the other? Because with F net, what you would do is you would set all the upward forces equal to all the downward forces. We don't know two forces, there's two unknowns. This is where setting your axis of rotation is really powerful, because what you can do is you can set it at one of your unknown forces. If I set it here, like what I originally had, this force no longer produces a torque. So in my torque net equation, if I'm looking at all the torques, about that axis of rotation, it doesn't produce a torque. So we can say that the torque, and then we just do all of our torques. I'm going to say clockwise is positive. So I'm going to say, okay, the torque by F kid plus the torque by Fg minus, this is in the opposite direction, the torque by F2. Alright, So that's how you can figure out the torques and stuff. There are all sorts of rotational equilibrium problems. You can have problems with the ladder, and you can try to figure out what is the force friction on the ladder, and then if it's not like rotating and stuff like that, and then you would have to draw in all your forces and figure that all out. There's all sorts of problems with this kind of stuff. And my advice is just practice. Search up rotational equilibrium practice problems. Practice this kind of stuff. I could go all day talking about them, but I got to move on to now angles, because now these things can have angles, right? So the main thing conceptually to really think about angles is, like, imagine a door, right? If I have a top view of a door, I know very well that I can't, if I apply a force here, nothing is going to rotate. Like nothing is going to rotate, right? Because I'm going at the very side. I need to apply a force this way. So already we can figure out that if the force is kind of parallel with the lever arm, or like with the distance, there's going to be no torque. It's not going to start rotating. Same thing with the with the perpendicular force. Now there is going to be a torque, and really what we got to learn is that only the perpendicular part of a force creates the torque. If I have a force angled, there's two components: the parallel part and then the perpendicular part. We know the parallel part won't cause any torque. It has to be only the perpendicular part. So force perpendicular. How do you figure out that perpendicular force? We got to use trig, right? What angle do you know? If you know this angle, it's going to be like the sine, because it's like the opposite. If you know this angle, it's going to be cosine, because that's like the adjacent. Now the shortcut for figuring out like what's the perpendicular stuff is going to be doing torque. So if you had torque, right, is going to equal force times the lever arm. And the lever arm is always like the perpendicular distance. What you can do is you can just do torque equals force times r times sine theta. How do I know if it's cosine or sine? Well, sine 0 equals 0. So when the angle is 0, everything is 0. There's going to be no torque. If we had cosine 0 is 1. So torque is equal to force times radius, but there is no torque when the angle is 0. So that's how I remember if it's sine. Now the angle always has to be the angle in between. So if you always have to do like this angle and the angle in between the force, right? The force and the distance. So if they give you, so let's say they give you this angle, like with the vertical, then it's not going to be the right angle because you need the angle in between. So you'd have to do 90 minus theta. That's where I'll really end with angles. There will be problems where you might have to find, like if you had a wall, you have to figure out the tension force, right? And then you have to do torque times force times lever arm, which is going to have that sine theta. But it's the same skills with equilibrium. So I'd say practice equilibrium problems, get used to angles as well. Yeah, that's kind of it with torque in terms of that equilibrium stuff. That's like a whole 23 minutes on torque. I don't know if I want to make a part 2, because I have to talk about rotational kinematics. I don't know if I should wait, because I have to talk about rotational inertia. Okay, I'm gonna make a part 2. So sorry about that. I don't like making part 2 that much, but this is such a long unit. So I really wanted to talk about rotational equilibrium in detail. So I'll talk about rotational dynamics. So maybe this is like the rotational equilibrium part. I'll talk about when things actually start rotating on the next video.